Okay, so everyone, thank you for coming in. So today, a few announcements before we get started. First things first, what was I going to say? I can't remember. Oh boy. So first thing I'll say is that today, so for this unit in particular, for Unit 10, a lot of people are going to miss a lot of things from this unit, right? There's a lot of testing, a lot of AP testing going on. And I think tomorrow, actually, all the juniors will probably miss a lot of class, right, because of AP Lit. So what I'm going to do for this unit is I'm going to record some of these lectures, and then, actually the entire unit, and then I'll put it online because I want to, like, make sure that you see it. Now, what that means is that the responsibility is going to be on you. That if you're missing a class, you need to come in here, pick up the notes for that day, so that then when you can go home and then watch the video, or if you want to, I can come in here and even project it for you if you would also like to do that. We can make some time and space for that. All right. So is anyone confused on that? Okay, go ahead.
Let's just let you know that Graphically is going to add on the video. Are you class for tomorrow?
Yeah, exactly. So for instance, everybody would be able to watch that video and kind of get caught up, right? There's not enough time. We only have like a week and a half, and then we got to go into common assessment review. I wish we could kind of a little deeper into these topics, but again, the whole point is to we got to keep moving along, so the videos are going to kind of help us keep at the pace we're going. Okay. I can't remember. Oh yes, the test. So I'm working on getting that graded. The curving tool hasn't come out yet. I'm still waiting for that. Should be by the end of the week, if not by Thursday, if not by tomorrow. Probably Thursday is realistic though. Alright, so let's take our first unit of lesson 10.1, which is an introduction to calculus. Now, I know a lot of people see that word calculus and they immediately think, oh my god, this is too hard, right? But here's the thing, two things. First of all, we're only going to be touching calculus very lightly. So we're not going to go into the first derivative test, second derivative test, related rates. We're not even going to actually talk about integrals. We're just going to talk about the very, very front of calculus. So it's going to be very introductory. Second thing is that calculus actually is somewhat easier than pre-calculus. Because pre-calculus, you're kind of getting in the guts of stuff. And as we'll see, calculus was actually made to make some questions easier to answer mathematically. But anyway, so the first few minutes of this class is going to be kind of a lecture style, so I'll try to bring everyone. So anyway, so let's kind of make a framework for when calculus was invented, right? So calculus was invented in or not invented, I should say discovered, in the late 17th, early 18th century, right? Now, what was going on at that time? Who was like the big authoritative power in the late 17th, early 18th century? Not Rome. Not the Aztecs. Not the Byzantine Empire. Who was the big authority at that time? Go ahead.
The church.
Yeah, the church, right? The church, especially the Catholic Church and the Pope, right? The church. And that church gave the kings and queens their legitimacy of power, right? And so, what mathematicians and scientists came along and began asking questions is, well, for instance, what was the normal explanation for why? So, do y'all know how do the planets go around the sun, and what sort of shape? Not circular, oval shaped, right? They go in. So the question was, why was that the case? Right? Why was it the case that, and what was the typical explanation? What was that? God made it that way. God in his infinite wisdom that we will never comprehend made this world so that, it's just that way just because it is, right? He was a watchmaker, right? Ever hear of watchmaker theory? You might have heard of deism. But anyway, scientists began asking at the time, well, no, what if there are mathematical laws and explanations that actually can explain those things? What if there's like kind of equations, and what if there are things, right? And so eventually out of this, Newton, to answer these questions, actually developed calculus, and then from calculus, all of the equations that you learn in physics started becoming developed. So, that's a small introduction to calculus. So anyway, go ahead.
somebody just like sat down and just like thought all of this stuff? Like they just
What's that?
thought about all this and just created it?
Well, what Newton and Leibniz did when they kind of discovered calculus was, I believe Newton would kind of just observe how basically Newton's whole deal was, he saw an apple falling from a tree, right? And he observed that there was some force that was pulling it, which was what? We know that force is called what now? Gravity, right? And it was thought, well, what if the force that is keeping that apple attracted to the Earth? What if that's the same force that's the reason that the moon is going around the Earth, right? And even further, what if that's the force that's keeping the planets actually revolving around the sun, right? And if it is the case that it is some natural force that we can conceive, is it possible to write equations, to write mathematical equations, to describe that force, so we can describe how things move? And again, he thought of those questions, kind of observed what was going on, and was able to kind of make these equations that seem to explain why these things were happening. And they fit pretty well. In fact, when in the 20th century, when we got telescopes and measuring tools that had the ability to kind of measure these things finally, it was found that yes, Newton was actually correct most of the time. He was correct most of the time. And in fact, when NASA kind of creates calculations to go to the moon or send things to Mars, they frequently use Newtonian mechanics. So anyway, there are two questions that mathematicians and physicists kind of struggled with at the time that calculus helped us answer. The first was something called the tangent line problem. Now, as you can see, what this problem basically says is if I have a function like this, and I draw a line between the two functions, in Algebra 1, you've always learned what is the equation of the line. Yeah, this y equals mx plus b, right? That's the equation of the line. Now, the slope of that line, the m, is rise over run, right? So what I do is I take y2 minus y1 over x2 minus x1, right? We've all done that. We've all done that in a algebra course. Now, here's the thing. If I want this line, right, which we call this line the secant line, right? If I want this line, I just do that. I just take the function, the two y's over the x's, and it'll give me the slope of the secant line. But let's say instead I don't want a secant line, I want what's called the tangent line, right? And why do we call that line the tangent line? Why do we call that line the tangent? What does it mean when you say someone goes off on a tangent? They kind of are on a topic and then they just kind of take off somewhere else, right? This line is kind of doing that, right? It's barely touching the function at that one point, but then it kind of goes off, right? Now, but at that one point, what is this line giving us? It's giving us the what of this point. What is this line? What was the mx of this line? What is the m of this line? What were we getting the what? The slope. So what is this giving us? The slope of what? The slope of a single point, right? This single point on the graph has, the curve has a single point, right, where it's touching it. But here's the problem. If slope is rise over run, what's the run of a single point? 0. What's wrong with that? You're dividing by 0. You cannot define a single point. You can't have a slope at a single point. Or so it would seem, right? Or so it would seem. You can't have a slope at a single. So that was the first problem. And we're going to kind of dive a little more deeply into this. Second problem is what is called the area problem, right? Now, we all know from Miss Tang's class when she was here, what is the area of a rectangle? Length times width. Duh. Right? Here's the problem that mathematicians struggle with. What's the area underneath that curve? Right? How do I find, if I want to make more complex structures, right? If I want to do architecture, if I want to do engineering with more complicated things, how do I find the area underneath this? Right? There's no equation, there's no simple. what's wrong here? Well, the line here is changing. It's not like a rectangle where it's just constantly on top. This is changing. The height is constantly changing. The width is constantly changing. So how do I find area of some sort of shape that does that? That constantly changes its length and width? Well, eventually what was figured out was that I can actually slice this area into smaller pieces, right, into smaller rectangles, and then get an approximation of what's under there. But then I can slice it, keep slicing it further and further, and what's the most I can slice it to? What's the highest if you just keep slicing it forever? Infinity. I can slice it into infinite pieces, and I will actually get the area of the curve, right? And so the big breakthrough you made in mathematics was something called the fundamental theorem of calculus, which connected these two topics, these two questions that were completely unconnected. Newton and Leibniz connected them independently at the same time. Now that's crazy, isn't it? Right? Think about that. Think about if your friend, right, if your friend said, hey man, I figured out this cool new way of doing this thing, right, of like kicking a soccer ball or whatever. And then at that exact same moment in history, your other friend was like, yeah, I actually figured out that exact same thing. So it makes you wonder, did they invent calculus? Or did they what? Discovered it. Maybe these are laws, these are things that just are dictated by the world. This is just true no matter what. If two people came to the same conclusions without even talking to each other, with no communication, doesn't that kind of mean that maybe this is right and true? Right? Possibly?
What are you saying?
I'm just saying that, because some people question, like, well, math, like, this is just stuff we made up to, like, make math students' lives harder, right? But if people are coming up with things independently, it may be the case that, no, this actually is how the world works, right? But anyway, whether or not you believe that, it's true, so. All right. Let's go ahead and turn the page. So we're going to focus on the tangent line problem. Okay. So again, this problem states that if I have a secant line here, and I want, again, what's the problem with wanting a tangent line or wanting the slope at a single point? I'm dividing by what? I'm dividing by 0, right? I can't have this function have a 0 on the bottom. But here our friend Isaac Newton on the right, who we also know from Newton's laws, he's saying hi. What question is he asking there? Yeah, why don't we have a concept, a mathematical concept, where rather than dividing by 0, we divide by a number that's really, really, really 0.000001, right? Something that's really, really close to 0, in fact, so infinitely small that it essentially is 0. What if we divide by that and create instead of dividing by 0? Am I violating any rules there? No, because I'm not dividing by 0. But I'm still kind of dividing by 0, right? So, what do I mean by that? Well, let's look at this problem. So here I have this function. F of x is equal to x cubed minus 1 over x minus 1. Now, why can't I plug in 1 there again? What would happen if I plugged in 1? It would be undefined, right? I'm dividing by 0. But the question is, why not? It has to have some value of 1, right? It has to go somewhere. It has to be somewhere at the value of 1. So, what we can do is this. Let's try getting really, really close to 1 from the left and getting really, really close to 1 to the right. So on x, we get 0.75, 0.9, 0.99. So we're getting really, really close to 1, right? But we notice as x approaches 1 from the left, what does it look like f of x is getting close to? 3, right? And if we approach x from the right, so 1.25, 1.1, 1.01, 1.001, what does it look like it's getting really close to on the right side? 3 also. So it looks like as this function, as x gets closer to 1, the function is spitting out what gets closer to what? 3. What's up? Huh? Yeah, we did in algebra. We also did it a little bit earlier this year. But I'm relating it a little more to calculus rather than just like hand waving and being like, learn this. So what's up?
What's like the smallest object like in the universe?
The smallest object? Well, that's a good question, because we used to think that it was electrons, neutrons, and protons, but now we're finding out that there's something called quarks, which are what composes an electron and a neutron. So those are the smaller things now.
There's something smaller than quarks.
There might be something, I think there actually is something smaller than a quark that they figured out. So that's a good question, right? At what point? Because that's an interesting question, right? If you chop down something to its smallest small, at what point does it become like an object, and what point does it just become nothing, right? Like, how small does it have to be before it's just like you're holding nothing in your hand versus something? Anyway, so that's the basis of what's going on here. Is that I can get close and close and close to this number, and it looks like it's going towards a value. But if I actually plug in the 1, what happens? Nothing. It's undefined, right? If I'm driving there, I'm like, yeah, I'm going to 3. Right? I'm going to fall in a huge hole, and there's not going to be anywhere for me to go. Okay, so I'm sure everyone's like, when is he going to shut up and when he's going to start doing math? That time has come. All right. So, let's talk about estimating limits. Let's talk about estimating limits. And again, everyone, please make sure that you have your attention up here. This is the first lesson in the unit. You really want to make sure you get this down so that everything else from the unit starts making sense. Okay, so what we're going to do is this problem says I want you to find the limit as x approaches 2 of negative 3x plus 1 using a graph and a table. Okay, so we're going to find the limit of negative 3x plus 1 as x approaches 2 using a graph and a table. Okay. So first, let's do a table. All right. So what I'm going to do, I'm going to make what I did on the last page here. Here I go, making a table again. Okay. So there's x and f of x. In the middle, what do I want to approach? What value for x? 2, right? I want to approach the value it's telling me to approach. So I'm going to put a 2 here. I don't know what f of x is at that value. And then I'm going to input 3 values to the left and 3 values to the right. Okay? So we have that. All right. So first, let's talk about when x approaches 2 from the left, right? X approaches 2 from the left, okay? So someone give me a number to the left of 2 that's right next to the left of 2.
1.9.
1.9, perfect. Okay, 1.9. Now give me a little bit closer.
1.9.
I think you all see where this is going?
1.9.
Right. Okay.
1.98. It's pretty close. But not there, is it?
Yeah, exactly. So, in case you've forgotten how to enter numbers into functions, remember what you do is you say, okay, I'm going to say, let me do it up here. So I'm going to say f of 1.9. I enter 1.9 into this, so it's going to be negative 3 times 1.9 plus 1, just to remind you of what's going on here, how I'm getting these numbers. And that's going to come out to be negative 4.7. So the function at that point will be negative 4.7. Just a quick reminder. So anyway, I plug in these x values into this function. So I say this is going to be negative 4.97. This will be negative 4.99. Okay. So, as x approaches 2 from the left, it looks like f of x approaches what? Exactly. F of x is approaching negative 5, right? So as x approaches 2 from the left, f of x is approaching negative 5. Now take note, we're not at 2, we're just approaching 2. And then we're just approaching -5. We're not there. We're just approaching it. Now let's look at the right side. Give me a number really close to 2 on the right side. 2.1. Closer? Closer? Good. So x approaches 2 from the right side. X approaches 2 from the right side. And so, if I plug that value in, if I plug 2.1 in, let me just kind of plug in my computer here. If I approach it from the right side, 2.1 will give us -5.3 if I input that into our function, -5.03, and -5.003. So again, let me ask the question. What does it look like this is approaching? -5. As x approaches 2 from the right, f of x approaches -5 as well from the right, right? So, it appears that this function is both approaching from the left and right -5. What's that?
Maybe make -5 equal to that equation.
Equal to this?
Yeah.
Well, that's a good question, because let's draw the graph and then I'll answer your question, all right? So, I promise I'll help one. So, let me draw the graph of this just to kind of illustrate a little, again, what's going on. So, if I graph this out, my x and y axis here, my y-intercept of this function is, anyone know? What's my y-intercept? 1. So it's going to cross there at 1. And then it has a slope of -3, so it's going to look something like that. And of course, this line is the function f of x is equal to -3x plus 1. Right. Now, if I look at the point 2, and I approach that point and I get closer and closer to 2 in the x value, what value should I be getting closer to here on the y-axis? -5, exactly. So graphically we also see that as this number, as x gets closer and closer to 2, we're approaching closer and closer to -5, right? We see that graphic. Now to answer Chris's question, is this function have a value at that point 2? Can I plug 2 into this? Can I plug 2 into this? Yeah, -3 times 2 is? -6 plus 1? -5, right? So this value at this point actually exists, but we're not talking about that. We're not concerned with that. We're looking about the limit as it approaches that point, right? So the value is there. It's just we're concerned with what is it approaching rather than what is it actually at that point. Does that make sense? Okay. All right. Cool beans. So now that we've done that, go ahead. We're going to take about 5 minutes. Let's do a CFU. Go ahead and do what I just did, but do it for the limit as x approaches -3 of the function 1 minus 5x. Now, if you're going to graph this out, you can use your graphing calculator. It's totally viable option. So, go ahead and take about 5 minutes. Go ahead and do that. So you're at negative 3. What number's to the left of negative 3? Negative 3.00, right? Be careful there.
No, it's bring it back, you just looked at my paper.
Yeah, it's like when you're not observing them, for some reason, you would red or weird, right?
Okay, now I know.
All right, let's look at this. So, this is our answer. So, again, I drew the picture here first just for the visualization. So this has a y-intercept of 1 and a slope of -5, so I drew it like that. Now again, as we get closer and closer to this value of -3, it looks like we're getting closer and closer to a y value of what? 16, right? On the graph, we're getting closer and closer to y equals 16. As x gets closer and closer to y equals x equals -3. Again, as we mentioned, if you actually plug in -3, you will get 16 here. But again, we're only concerned with what is it approaching, not what is it at that value. The one trick, or the one thing I wanted you to watch out for was be careful, because this is -3.1. Some people put -2.99, but that would not be to the left of it. That goes on the other side, right? Now, so, yeah, ignore this stuff right here. So, just, yeah, ignore it. Okay. So, right here, when I plug in -3.1, 16.5, -3.01, 16.05, it looks like both of these sides are getting closer and closer to what? 16, exactly. So the numbers themselves, as x gets closer and closer to -3, f of x gets closer to 16, exactly. All right, let's keep powering through to the next. Now, why do we care about this, right? Why do we care about what it's approaching when we can just as easily, plug in the number and see what it is, right? Why do we care about what it's approaching? Well, the answer is that in some cases, it's going to be the case where they may not approach the same value from both sides. And we have to decide, well, what are we going to do in that case? How do we say what is that limit, or what is that function approaching at that point? Okay? So, let's go ahead and turn. Go ahead and turn. And we will talk about the famous topic. We'll talk about when limits don't exist, right? Sounds like a documentary you might see in an English class. When limits don't exist, right? Yeah, exactly. Let's look at this function. Let's say that the limit as x approaches 0 of 1 over x, right? Let's say we're trying to find the limit as x approaches 0 of 1 over x. Now, what's the big deal with this? Why is this a concern? X cannot be 0, right? Why?
Because then it would be undefined.
Exactly. Then it would be undefined, right? We can't divide by 0. But we can do what?
Get close to 0.
We can get really, really close, right? We can take Newton's suggestion and get really, really close to 0. So let's do this. So I'm going to go ahead. Let's go ahead and make a chart or table. There we go, making table again. All right. So f and f of x. I want my value I'm approaching in the center, and what value is that? What value am I approaching? 0. Okay, I'm approaching 0. I don't know what this is. All right. So, what is, give me a number to the left of 0. Point. We get closer than that. 0.001. Okay. Negative 0.001. Let's get a little further away so we can kind of build up to that. So I want to go, 0.01 and then 0.1, right? So I kind of want to show the pattern too, right? Make sure that you pick numbers that show the pattern. What about to the right of 0? Positive, right? We just do these but positive, right? So it'd be 0.001, 0.01, 0.1, right? Okay, so let's start from the left. When I divide 1 by negative 0.1, all I'm really doing is moving decimal places, right? So this is going to be negative 10, negative 100, and negative 1,000, right? Negative 1,000. Now, here's the thing. So that means from the right side, or from the left side, sorry, what does it look like this is, as x gets closer to 0, what does it look like f of x is doing? It's just going, like, just getting smaller and smaller. Not just to infinity, but to what? If it's getting more and more negative, it's going to negative infinity, right? It's going to negative infinity. And so, how do we show that? Well, we say that the limit as x approaches 0. Now, can't say that the limit itself, we can't say that the limit itself is going to negative infinity, because we're only approaching it from the left side. So we need a symbol that represents that we are approaching this from the left side. And so what we'll do is put a little negative sign right to the right of the 0, or the number that goes in that spot, and that indicates that the limit is approached. Totally misspelled that from left. Approached? It's supposed to be approached. I think it's like a C, right? With an A there. Yeah. So, the limit as approaches 1 over x is, again, what happens when you approach it from the left? What is it? Negative infinity. Okay, negative infinity, good. Now, there's more. When you approach it from the right, now let's think about this logically. Again, these numbers are the same except they're not negative. So that means I should get the same values except what? Positive. So this is going to be 1,110. Right? So get closer and closer to that. So for this we can say that the limit as x approaches 0, but I'm approaching from the right, so what do you think is going to go after that 0? A positive sign, right? Now I will say, this is not saying that 0 is positive. It's not negative. It's just indicating what direction we're approaching it from. So don't confuse that. So this is saying that the limit approached from right, 1 over x. So when I approach it from the right, what's happening? It's going, as you get closer to 0, what is f of x doing? It's going to positive infinity, right? It's getting bigger and bigger and bigger. It's getting larger and larger and larger, shooting off to infinity. And so, let's think about this for a second. This function, as I get closer and closer to 0, is it like approaching a single value? No, it's approaching what? Two completely different values, right? If I was like driving, and I was meeting my friend along this function, I was driving, right? So if I drew this function out, this function looks like this, right? If I was driving this way, and I drove that way, would I ever meet my friend at any point? No. I would just keep going off to positive infinity, he would keep going off to negative infinity. So because from both sides we're getting two different values when we take the limit from two different sides, we say that this limit does not exist. We say that this limit does not exist. And so, what we say is that a limit does not exist, just like Mean Girls, if it approaches different values from the left and right side. So it said a limit does not exist if it approaches different values from the left and right sides. Okay. All right. Any questions? All right, cool. So I think we'll call it So on the next page, you have some homework. Now it says graph and table. So for graphing, use your calculator to graph it out. Do what we did in class. Number 4 is a bit of a challenge because it's a piecewise function. So I'm only expecting you to do the first 3. Shh, don't want to miss your homework assignment. I'm only expecting you to do the first 3. But if you want a challenge and you really want to understand what functions are, I would do 4. And so this is going to be due on Friday, which is going to be May 6th. Right? It's going to be May 6th. And also at the bottom here, I put a key, and that tells you what numbers this should be approaching. What numbers these should be approaching. All right. That is it for today. What's up? And sorry.